school or other schools are represented too?
Both our school and other universities.
Ah, I see. That's great.
So the journal is growing interest.
Okay. I hope so.
Oh. Have you ever met the editor, the chief editor of the journal, Professor Sochi Kyang?
Yes.
Nanyang Technological University.
Okay. Oh, he's Nanyang. Yeah.
Yeah, Singapore. Okay.
Great.
He started working in our school about 5 years ago, I think, full time.
Yeah.
After he retired from NTU.
From which university was he hired from? Nanyang.
Nanyang Technological University.
I see. Do you have, with this urban life, do you have a journal also associated with it? Is there a journal as well?
Yeah, it is a journal.
Oh, okay.
It is a journal. And
so this is on the side of the journal work, right? So people come in and present their work, right?
Yes.
Okay.
This is the series of activities that we're trying to expand the visibility of the journal.
I think it's a wonderful idea. I think it's a wonderful idea because you get to, the students get to see some of the people and you put a face to the paper or you put a face to the mentality, and it would maybe give me a chance also to show why I do some of the things that I do the way I do it. So it helps, I think.
Yeah. Engineering structures, the Journal of Engineering Structures, they do this a lot.
Yeah,
they do this for 3 years, I think.
Yeah.
How about we wait for another a minute or two?
Okay.
I always want to attend national conferences, but traveling abroad is complicated was in the past few years. But I will try to attend some this year.
Yeah, you've been busy. I haven't seen you in many of the conferences that's been going. We had a good conference in Germany with Victor McCharine.
What?
That was, remember you came to the meeting that we had in
Italy.
I want to think. In Germany. No, it was in. No, this is in Germany. This is a BFIP conference. The one in 2020. I think you went there. That was right during the COVID. In Valencia. So this was a follow-up, 3 years post Valencia meeting.
I went to the one in 2018, the one in Italy. I went to that.
Oh, okay.
Yeah, and then I went to Singapore in 2019. Yeah. And after that, that was the last time I went abroad.
Oh my God.
And I went to Singapore, but I've never been to Europe or America in the past several years.
Yeah.
It was difficult.
It's been crazy here.
Okay, I think now we have more than 100 audience. I think we can start. Right? Okay.
Great.
Good morning, everyone. It is my great pleasure to welcome all to today's seminar. Welcome engineering and the future of infrastructure. The topic is reinforcement in structural concrete perspectives on the sustainability of a century of design. Our distinguished speaker, Professor Barzin Mobasher is a leading scholar in the field of structural and materials engineering. He is a professor at Arizona State University's School of Sustainable Engineering and the Built Environment. He holds a PhD degree from Northwestern University. Professor Mobasher has led programs involved with design analysis, material testing, and full-scale structural testing of construction, structural, and aerospace materials. His publications include 2 books on fiber and textile reinforced concrete, 5 edited books, and more than 220 research papers in leading journals and the conference proceedings. His fundamental contributions are in the analytical and experimental fields of fiber and textile reinforced concrete. Their applications areas and the mechanics of toughening in UHPC, TRC, durability modeling, and experimental mechanics. He has served as the chair of American Concrete Institute, ASAC Committee 544 on fiber reinforced concrete, and technical activity committees of both ECA and RANA. He is a fellow of both ECA and RANA. Last but not the least, he's my master and PhD advisors. Today, he will share insights into hybrid reinforcement systems and advanced materials like UHPC and TRC, and the novel design strategies that enhance durability while minimizing resource consumption. From reimagining building codes to pioneering fracture mechanics models, Professor Mobasher's research promises to redefine how we approach structural efficiency, sustainability, and economic benefits. Please join me in giving a warm welcome to Professor Barzin Mobasher, who will now take us a journey through the past, present, and future of sustainable concrete design. Okay, Professor Mobasher, the floor is yours.
Thank you so much, Professor Yao. It is an honor for me to be invited to present at one of my favorite colleagues that I have had the pleasure of working with him. That's Yiming Yao. I think if you have any questions, I think you should ask him afterwards, because he's the one who would know a lot of the work that's being presented here. And I think he used to be my right-hand man in terms of ideas and working together. And I do miss working with him now that he is there. But I think you have to appreciate the fact that he is there providing for you. I want to talk about the subject of reinforcement in structural concrete. And part of my motivation is to look at the value that reinforcement gives concrete. And then at the same time, a lot of the effort, if you look at it from concrete's carbon footprint, a lot of the effort has been placed in the area of cement substitution products, a lot of new cements and formulations and such, but very little is done in the area of how are we designing the reinforcement, how are we calculating it, what are the methodologies that we should use, and what are the alternatives that we have available. So this is the mood of my talk. I want to focus on concrete, but I want to look at it from the way we look at the reinforcement aspects of it. So with that, I want to, let me see if I can, I don't know if this monitor is showing on my screen, if it's also showing it on your screen as well, but okay, great. So I want to say that the concrete consumption is unsustainable. That's the first part that I want to say, because we use 30 billion tons of concrete every year. That is almost more than 3 times the number of people who inhabit the earth. And if you look at some of the statistics compared to all countries, concrete industry is the 3rd largest CO2 emitter, and somewhere about 8% of the world's CO2 emission. That's without even counting the steel, because the steel is almost as much. And there is tremendous amount of opportunity for us to look at this problem. But when we look at these technologies of carbon capture, storage, or mineralization of carbon dioxide, it is still we still don't have a lot to show. $27 billion have been spent since 2017, and we really don't have a very powerful industry to address that. So we need to look at the way we look at concrete and the way we design concrete. And the second item that I want to mention is that we are using significantly outdated design procedures. Some of these ideas that are presented here in these publications and news show that there is a real serious need to address that in the concrete. And the question is, are we doing enough? Because I believe that there is a changing societal attitude toward use of concrete. And there are articles that come out that say, for example, concrete is the most destructive material on earth. This is giving us a bad rap, bad idea, that this is not right, that when everybody comes in and they want to just blast concrete as a fact that it's a problem, or the false promise of carbon capture as a climate solution, where oil companies, they take the carbon dioxide, pump it into the ground to get more oil out. But that carbon dioxide, there is no guarantee that it's going to stay inside the ground. So we need to look at our consumption. For example, China's cement use in 3 years was more than what US used in the last 100 years. And the growth of the Chinese economy, transportation, infrastructure is really dependent on how well concrete has been used. But we really need to, and I do want my colleagues there to take a lead over some of these ideas. And if there is any way we can discuss these ideas, I would be grateful. The idea is that my third question is that about 60 to 75% of the concrete that we use is loaded under flexure. And because of the fact that its tensile strength is so low, it doesn't really carry much load. The magnitude of the load or stress that concrete carries in tension, as you all know, is quite small. So how do we develop some efficient designs for the concrete? So that's the next idea. Are we doing enough in order to develop efficient structural designs? And of course, we need to start looking at and I want to call it a monopoly of steel that is used as the only material that's used for reinforcing concrete. Yes, we're using composites and everything, but the total amount of all the carbon fibers and the alternatives that are there is only about 100,000 tons. Whereas when we talk about steel, we use about 2 billion tons of steel throughout the world. And that slide is shown in here. When you look at world production of steel in the past 70 years, basically from 1990 till today, the amount of steel that has been used has been tripled. So no matter how much we recycle steel, we're still, our consumption is much higher than our rate of recovery. China produces 1 billion tons. Half of this amount that is happening today, half of the amount is produced by China. But 25% of all, which means that that's somewhere about 500 million tons, is only used in the reinforcing concrete. So 25% of all of this number goes into concrete as a force of reinforcement. But we have all of the problems as far as corrosion, all of the problems as far as the labor costs and the amount of value. So if you want some conversion factors for every cubic feet of concrete, and we can convert it into SI, there is about 7.5 pounds of steel rebar that's used. So steel contributes as much carbon footprint to the concrete as much as concrete, but nobody's talking about how are we going to find alternatives for steel. And so that's basically the area of my work. So how do I reduce some of the steel that's used so much? So here you can see this is a dam picture from Brazil, and you can see some of the giant structures that are being built, and the amount of steel is unfathomable as far as how much we're using. So my goal is to look at this particular mode and address it. So how are the strategies? One of the things is that the efficiency, I want to look at the efficiency of concrete from several points of view. One of them is the stress to strength ratio for both tension and compression. Concrete is extremely good in compression, but it's awful brittle and basically in tension, which means that we have a very low tensile capacity. So we need to look at normalize the specific strength. We need to be able to characterize the material property not based on its compression properties only, but also the tension properties. If we can improve the tension properties, we can definitely carry a lot more load, because tension failure is the dominant mode that is a showstopper that doesn't allow us to further use the amount of concrete. So my argument is that we waste a lot of concrete because we allow it to crack in service, and then corrosion and everything comes. So we need to look at specific strength per volume, and we should stop looking at compressive strength as a measure of how much CO2 per MPa we're putting out there, because we never get to reach that level of this strength. So why are we putting so much more cement in order to increase the compressive strength, whereas we're ignoring the tensile strength? So what are the solutions that I have chosen throughout my career to address it? Well, let's look at fiber reinforced concrete, textile reinforced concrete, hybrid design, and also UHPC. So all of these areas allow me to increase the tensile strength of concrete. And it's not about really exotic, fancy work. I'm trying to see what areas we can look at where we would take the minimum reinforcement that the code requires, take that out and use fibers in there, and design the concrete such that using maybe polymeric fibers or other type of synthetic fibers or even steel fibers can work better. Now we can make steel fibers which are 3 times or so higher value of the yield strength or even stiffness. So we can make steel much more amenable for reinforcing concrete on a kilogram per kilogram basis. The next step, which I want to get your attention, is that should we look at the way we design it? So can we develop design equations based on resilient and also ductile type systems for all of these materials? So let's look at a little bit of lesson in history. The bridge that you see there, it's basically 125 years old. It was made in France based on the fundamental principles of reinforced concrete. So the ideas have been developed for more than 120 years. Model T cars, automobiles, were developed in 1908, and the first international flight, transatlantic flight, passenger service, happened in 1939. So look at this airplane and look at the current day airplanes that we have. At the same year, 1938, that's when the design of reinforced concrete became standard. And today, we're using a procedure which is very similar to the procedure that was developed in 1939, when this was the only mode of transportation for travel. And to prove that, I can show you this. These are some slides from 1907, which looks at the ultimate load calculation of a reinforced concrete with compression reinforcement and tension reinforcement. Pay attention to the tensile load that's only carried by the steel rebar, and the compression zone that's carried by the steel and also concrete. So this is very similar to what we do. Even the conventions of D and KD are still, and D prime are exactly the same that we do. One other point I want to mention is that if you pay attention, the location of the neutral axis is calculated by a parameter K, which is the solution of a quadratic equation. So to solve this problem, they only had to solve a single quadratic equation. And I believe that even today, in all of our reinforced concrete designs, we're teaching the same approach, one quadratic equation to calculate the neutral axis. So this procedure was developed along all these years, and now we're using ultimate strength method, which goes back to Charles Whitney's block diagram, which was developed in 1930s. So this is the solution that we're all too familiar with. In every brand new book, we would see that we would set up and solve this equation for this stress assumed distribution. Still, concrete is not carrying anything. Neutral axis is above. Except there is one thing I want you to pay attention. This is a schematic diagram. This is not exactly to scale. And what I'm trying to do is to plot this diagram in scale and at the same time try to see how much load I can get to carry by the concrete if I put certain amount of fibers in there. That's my goal. Another goal that I want to address is that everything we have done up to now has been from a macroscopic point of view. Look at electronics industry, how they have gone to the microstructure, how they've used material science. And the question is that we reinforce materials this way, and we expect that about half a meter away, a crack that's forming, a rebar would sense the load that's applied on it and reduce the stress on it by carrying that load. This is not going to happen. This concrete has to fully crack before the rebar even gets activated and carries the load. What that means is that we have a fracture problem that we need to solve. And that fracture problem means that we cannot allow all of this concrete to have a crack that propagates through it all the way. We go to fiber reinforced concrete, that we get a tremendous performance out of it because we're reducing the size by basically a matter of almost 1.5, 2 orders of magnitude the size of reinforcement. So now the fiber is very much in close proximity. We can go 1 order of magnitude more. Now if you're doing textiles, and these are polymeric textiles with a material that is much lower in stiffness, we get 10 times better performance and improvement in the properties of the concrete that we're using. So in my opinion, going with textile reinforced concrete, we're doing a reinforcement at the microstructural level. So the difference between these is the following. In the case of rebar, we have an delayed activation of reinforcement. Your reinforcement doesn't kick in, doesn't carry load until there is a full crack widening at the concrete, and it allows all these ionic systems come in. But in the area of fibers and textiles, we have what we call an inhibited localization, meaning that they are preventing localization from taking place, so the concrete is carrying a lot more load. I'll come back to this inhibitedness later on. So what are the potential mechanisms that I can toughen the concrete? Everybody has done this, and we know it, but the question is, how do we bring them into formulation? So one of them is crack pad tortuosity, allow the crack to go through so many different paths, deflect the cracks, make him just break apart and dissipate the energy, crack bridging, fiber pullout, yielding. All of these are negative energy. These are energy dissipation in the system. That's what we want. We want to spend so much energy, and that increases the toughness, which means that the energy required for growth of the crack is not available anymore. And the lamination cracks are perfect. At the same time, multiple cracking, tension, stiffening effects, and such, all of them become present, and they take energy out of the system. So that gives our structure a redundancy. We can go toward plastic limit states, and we can actually do the correlation calculations of how much more energy is needed to create all these new surfaces, to create all of this energy dissipation. And that's how actually we can increase the strength of concrete in tension by doing so. Now, so some of the examples, cartoons, is that if you have a small crack before it has localized of a size 2A, if it intersects certain number of fibers, the only way you can deliver energy to the edge of the crack, to the tip of the crack, it is obtained by opening of the crack. But if the fibers are bridging it, then it basically doesn't allow these cracks to join each other, and it delays. And then when you go into debonding, now you're going to have to slide these cracks, these debonding zones, and that dissipates energy. And the sliding and opening makes it extremely difficult for us to deliver energy to this point in the corner where there is being dissipated there. So this is what I call inhibited localization. Another way that we can look at is that if a microcrack grows large enough to hit a fiber, it gets diverted, it goes through a delamination crack, then the crack goes around. Now that delamination crack becomes a tunneling crack, which now propagates up and down. This up and down means that now you have 6 cracks, tips that they want the energy. So some of the items that I've written here, if you look at the slides later on, you can see these are all mechanisms that we can benefit from. This is good if you have fibers in there, if we try to look at the microstructure from material science point of view. And I want to tell you one thing. None of these mechanisms occur with concrete if it's in an unreinforced at the microstructural level. Because for this initial microcrack to propagate, if there is not a barrier along the path, this is just going to have all the energy to go through because the surface energy is so small for the growth of the crack. It's these nonlinear terms that generate and dissipate the energy that gives us the added strength. So this allows us to play with a system where we make composite laminates with different orientation of continuous fibers. This is the area of textiles that I will talk about. And when you look at the microstructure internally, we see all of these microcracks that have formed. We can also try to develop a sequential system where you have a fiber pull-out mechanism. You take the energy of that, you put it back into the system, and you try to calculate how much energy is required to grow this crack. Even when it grows, then you say how many more cracks like this top above I can put in there. So we get these parallel cracks. These count for doubling or tripling the strength in tension. And if you double or triple the strength in tension, you can definitely reduce the amount of concrete that's needed to carry a certain amount of load. That becomes secondary and we can calculate it. Another part that I showed you is how a crack gets bifurcated, gets deflected, and then travels. So this is basically all of the delamination that I was showing you in a picture. And these can be shown, all of these parameters can be shown are mechanisms that they form in the case of fatigue of metals. And that's how fatigue can be calculated in terms of how much damage you're allowing to take place inside the material. You don't want to have a clean, fresh crack that's growing. You want to basically make it difficult. Best example of it would be continuous fibers. So if you look at these pictures, these are microstructural pictures, and you see how the load from matrix goes as a bridge onto a fiber, travels across the crack, causes the delamination, and then sheds away. So technically speaking, any matrix that you see in here, although I have two sets of parallel cracks, any matrix here, the load jumps across here, jumps across here, jumps across here, and across here. Just like the game that kids play by jumping over a small stream and not get wet. That's how the load is being transferred through this path. And we don't take that into account. We don't provide for this. So any way we can do this would allow us to generate these parallel cracking. And the spacing between these cracks now is about of the order of 0.5 millimeter. So the crack width is kept smaller. The cracks cannot open up, so more cracks are forming, and so the bond issue becomes extremely important. That takes us into this area of manipulating the microstructure to make textiles with AR glass, polyethylene glass, with the woven. Polymeric materials don't have a good bond system, but if we can do this geometrical changes in there, this shape that we have, like a textile manufacturing, specific for our areas, they become extremely wonderful. We don't have to actually do that. Also, if we can go to micropolypropylene type fibers, now we're increasing the surface area. So cement gets in there, it dissipates, it forms cementitious products, it changes the microstructure. So now you have an anchorage system automatically developed in our system. These are areas that we should be working together. That's what I want. I really think that these ideas, we need more people to think that I can do that. I can do that. We can do this. This is much better and much simpler because we can see the effects very easily by running the tests. This is the interface zone of a glass. If we can fill up this interface with hydration products, with calcium hydroxide, that gives us a certain degree of bond. And I want you to pay attention. We don't get full bond in these cases, and that's okay because these weak bonds give us delamination, cracking. So I don't want perfect bond actually, because perfect bond would mean that the crack has no propensity, has no direction to go up and down and in different directions. I want damage. I want these to be directing the cracks. And that is obtained by these interlock mechanisms that we have. So we can look at polypropylene fiber or carbon fiber. So in all of these, what I want the pull out. I want energy dissipation. I am not really as much interested in changing the stiffness of the composite by carbon fibers. I could care less, because the cost of increasing the stiffness of the concrete is not that much important to me, because it's already stiff. I just want to prevent the cracking. I want it to, even if it cracks, I want it to carry 30%, 50%, 60% of its tensile capacity. Let me put it another way. I want to get only 3 or 4 megapascal tensile strength out of concrete. If I can do that, I can guarantee that we can do the numbers and show that we can get billions of tons of carbon dioxide out of our environment. So that's a humanitarian thing that we have to do. I don't want to make the strongest UHPC system. I just want to be able to activate these mechanisms. Now, what are these mechanisms? These are mechanisms or bridged cracks. And these bridge cracks can be represented by 3 parameters, and they are all related to each other. One of them is bridging stress, how much stress is being transferred through here. Another one is crack length, how long has this crack propagated, what is the allowable crack, and finally, what is the crack opening profile. So these can be represented by sigma, U, and X, the 3 parameters. And you can define stress crack width relationship, stress distribution along the face of the crack, or crack opening as a function of the position. All these 3 variables become really important in our calculations, because we can show that the force of the stress here can reduce the stress intensity factor that I would have in here. In other words, they transfer the load and they rob this critical point, the crack tip, from the energy that it needs to propagate. And at the same time, they can close it. So this is the part that I concentrate on, the fracture mechanics aspects, to be able to explain how the toughening comes in. Why is flexural strength higher than tensile strength? And how do I want to focus on these mechanisms? Because these mechanisms are really important. So the way we have been looking at these mechanisms has been done by looking at R curves. R stands for resistance. And the R curves basically allow us to look at how toughness enhancements form due to increase the resistance. So if I have, imagine you have a crack that's propagating and there are a bunch of fibers sitting here along the length. As the crack hits a fiber, the first fiber adds some extra energy. So the resistance, initial resistance, is increased by 1 fiber. If it hits the second fiber, now it's 2 fiber. Then it's 3 fibers. But by the time it goes through, now the first fiber also gets pulled out. So the first 2 fibers now are not carrying any load. So technically, I start with a resistance that's very low. As the crack is growing, this resistance is increasing in a nonlinear way, and I reach a point of steady state cracking. Now, steady state cracking is what basically everybody's used to. This is the fracture mechanics part. But look at what I have done. I have increased the amount of energy. By allowing certain amount of stable crack growth, I've allowed more energy for the steady state. So the material now has a toughness that may be 3 times as high as here. And that can be calculated. We've shown it in papers, several papers. That's a Green's functions approach that we can actually calculate it by loading unloading tests. And we can calculate how much toughening do we get from a strain energy release rate calculation or the R curve calculation. Both of these can be shown to be very similar. And these are methodologies that are used in the metals area for plasticity. We've borrowed these techniques from our colleagues. So this is not like my area. I'm just basically transmitting some of the information that I've learned throughout my years in here. So we developed a model about 35 years ago, and that basically tells me that I have a condition. R curve can be thought of as a condition of stability. In other words, I have stable crack growth as shown by this green curve, and that is basically my strain energy release rate as shown as function G from fracture mechanics. If I increase the load on the structure, the crack slowly grows by delta A until I reach a point where there is a slope of the 2 curves between G and R are exactly the same. So initially the crack incrementally grows and it stops, grows and stops. That's shown by R equals G, but the rate of resistance increases as the crack grows. So this is a stable crack growth. When I get into instability is when the slope of these two red and blue curves are equal to each other. So it's a very simple thing to do. And I developed this with my colleague, Professor Chengcheng Ouyang, at Northwestern University when we were working together. And the solution that we gave was actually a solution to a differential equation. And the parameters are two parameters. One of them is a parameter alpha A, which is the amount of growth of the crack from the initial notch. And the second parameter is the toughness of the material that we can define it as parameter beta. So with two-parameter model, we can actually predict how much does a crack grow and how much extra benefit do we get. And this method has been used for us to show the toughness increase when you put fibers into concrete. And this is done by means of compliance calibration, which is a standard procedure now for doing for measuring. So a good test for fracture measurement is this compliance calibration, where you get the R curves and you fit. And now you can say, well, this is I went from a level of 24 to 35 or so. And this is only using aluminum microfibers. So small fibers increase the fracture toughness of the material. Now, when we do that, we get basically the process that we call strain softening. That means that once I reach the peak, I don't have a fracture problem. I don't have a big, huge sound. The FRC material basically carries more load as it's growing. And that has to do with this fiber pullout because of the bridging fibers, which I mentioned to you. And that can be represented by a stress crack width relationship or crack width projection and all of the parameters that I talked about before. But this is basically puts us in a domain of strain softening. If I go with a higher amount like textiles or UHPC or such, now there is so much fiber in here that as soon as one crack forms, then there is more energy available for growth of second crack and third crack or so. So I get these parallel microcrack system. And that would mean that I go into a strain hardening response before I get into this softening. Now I'm increasing the strength. Now I'm having a material that its tensile strength is almost twice as much, and my stress crack width relationship could be treated as a plastic type of a curve. So this is actually really good, but it's costly. Let's say the cost of UHPC is defined by this model, whereas strain softening is for conditional standard conventional material. But the criteria for strain hardening is that we must get some kind of a stress parallel crack system. We should get fiber pullout that's controlled, and actually we can actually calculate the stiffness, and the stiffness reduction here can be used for our design. And this takes us back to this whole issue that it was developed, this area was developed in by Kelly in the book that he has, Strong Solids. And this goes back to what we refer to as ACK model, which was for brittle fiber, brittle matrix composites, which showed that if you have a system like that from energy principles, you can show that your stiffness decays until the continuous fibers carry the load. And we have shown that more than 30 years ago, that cement-based materials can be made this way. And this was done with, a long time ago, 1990, the paper came out, 35 years ago. So we need to capitalize on this, and we need to show why are these properties this way. For example, if we do the same material, tested in tension versus tested in flexure. So here is basically a flexural specimen, and we put a mirror at 45 degrees so we can stand in front of the specimen and see the number of cracks that have formed. And we see that we have more cracks in tension than in flexure. Of course, it has to do with the fact that a volume in the flexure is much smaller. We can use a Weibel approach in order to show that the system that we have is basically, because the representative volume in tension is much larger, probability of flaws are here. So that's one way to explain it. But we have a big problem with converting data from tension to flexural test. And that is an important parameter for us to look at. Why our cement-based materials show us a higher strength when we test them in flexure? Luckily, luckily, a lot of our failure designs, such as beams, are in the area of flexure. So that's where we look at. And for example, these are some data that we published a long time ago again, where the same specimen, tensile strength is about 5 megapascal, and the flexural strength is about 20 to 23. So if I'm designing something with this, I can design it with this calculation. So you see that these are the same. But the problem is I can't treat this value of strength, MOR, as an elastic equivalent stress. That's a big, huge mistake that we would make. It doesn't mean that I can design it with a tensile strength of 20 corresponding to this value. This is an equivalent flexural stress that we get out of the material here. So the challenge that we have is that how do I use a material that I know its tensile strength is 5 megapascal, but design it so that the apparent flexural strength is about 20. That's the key point in our work. Otherwise, we're going to have a lot of bridges that are going to fail because somebody thought that just because I tested it and in flexure I got 20 megapascal, I can apply 20 megapascal in tension also. So another parameter that we need to look at when I talked about energy dissipation is the fact and the manner that we test. When we test materials, depending on whether we do closed loop control or deflection control or load control, that affects the way the sample behaves. And the best way of looking at it is to run a test that's CMOD controlled. So we put a notch and load it, we get this blue curve. But the similar specimen, if I test it under deflection control, when the load is applied under a constant deflection measured by the LVDT, what we would see is that the response all of a sudden drops at this point. And this zone, this dashed area, is the amount of energy that's stored in the specimen that's given back to the test machine. What am I saying? What I'm saying is that when you load a specimen in flexure, there is so much energy stored in it that energy, the moment the crack initiates, and if it doesn't have a lot of fiber or a very small amount of fiber, that energy that's stored in the specimens is enough to cause the fracture of the sample. So many times we run into a test like this. The sample goes up, it hits a peak at the really concise place, but then immediately the load drops. This is not the full response of the specimen. This is because the material is so stiff and it cannot give the energy back to the test machine. It gives the energy back to the test sample. And that's what we refer to as basically what we call snapback, meaning that the load decreases as the deformation decreases, and then it starts picking up and going there. So this is basically a part of the problem that says that there is localization happening depending on how we're testing it. In other words, we just don't have enough fibers to give us that realistic strain softening effect. So with all of this background, how do I design it? How do I design concrete? So basically, looking at from a mechanics of materials point of view, I want to develop only using concepts of mechanics of materials and develop a 1D flexural response for a composite system. And if I do that, I need to respect 3 fundamental laws of mechanics. One of them is equilibrium equations. Newton's summation of forces equal to 0 in terms of statics, no problem. Second one, constitutive relationships. In other words, do not assume that the material has a strength. The material must have tensile and compressive responses in terms of stress strain. And I need to use those stress strain in my equilibrium equations to convert from strains to stresses and to the equilibrium. But the most important equation that's very much ignored is the compatibility condition, which is basically your plane sections remaining plane. And that parameter is also important. And how do we integrate all these 3 to be able to develop a 1D flexural response? But what I want to do is I want to solve the problems by means of closed form solutions. Because if I set it up in closed form solution, Anybody with a calculator can solve the problem. Anybody doesn't even need to solve an equation, because the closed form solution gives you the solution that you can just plug it in Excel or anything as such. So this is the traditional solution that ACI or model code or all these approaches use. And this is the approach that we chose to actually simulate this, except one thing, and that is we don't use this stress block. We don't go from strains to forces. We use the compatibility condition to generate the stress distribution. And if we do that, we find out that the difference between the strain distribution should translate into a stress distribution if I need to take into account the tensile capacity of the concrete. And that's how it would look. So the question is, how can I get these solutions in closed form? So to do that, we need to develop the stress distribution or stress strain diagram as a function of multilinear segments. Why is it multilinear segments? Because integrating a straight line is really easy, and that's what I want to do. But what I also want to do is to use the minimum number of variables. And by minimum number of variables, I want to define two intrinsic properties. One of them is the cracking strain, and the other one is the elastic modulus. So the product of these two gives me your cracking strength, and everything else after that should be a function of it. So if I have a slope that's positive or slope that's negative, I want to represent it by parameter eta. If I have a constant stress, I want to in the post-peak response, I want to call it parameter mu. So that's a number like 0.5, 0.6. Eta can be 0.1, which means that only 10% of the strain is retained after cracking. Also, compression should be expressed in this term. So I define parameter omega to represent the compressive strength to tensile strength. So its number is equivalent to, let's say, 10 or 12. So the concrete is 12 times stronger in compression than tension. The same thing for steel. So here is ES. Stiffness of steel is N times E. Or basically you can define parameter kappa, which is the strain capacity there. So now that I have very few variables that can connect to each other because everything is specified. So for this design, I need to first define my constitutive relationship, and we've developed about 6 or 7 different models of this kind, and each one of them addresses a certain area. So tension reinforcement, compression reinforcement, and we define different zones. So 4 pieces for tension, that gives me 4 segments, 2 zones for compression, that gives me 2 zones, and 2 zones for steel. So now I have a multiplication of 4 zones by 2 zones by 2 zones. And I have a strain distribution from my strain compatibility condition. And I have to use the geometry of the specimen that's defined in terms of here B and H, and also the location of the rebar. So all of these are variables that the designer can use, but they're all put in as a scalar. There is no dimensionality in this equation other than basically parameter E that is used. That's it. And everything else is non-dimensional. What that means is that I can set up these equations, and now I need variables. I need 2 variables. One of the variables is the maximum tensile strain, shown here as beta, and the other variable from here is the parameter K, which is the neutral axis. So if I know beta and if I know K, depending on which zone beta falls, I would know exactly what my strain is in the tension, but then I need an unknown of K, which tells me what my strain distribution is. And with the knowledge of these 2 variables, I can write the equations for strain in steel, strain in compression as a function of the tension. And I can set up every single equation because my strain along the depth is shown as a function of beta, which is shown as beta prime Y as a function of the depth. And that would give me all of the forces. Now I define also the points of interest, like, for example, compression, strain in concrete, rebar strain in compression, rebar strain in tension, and tension. So these are all points that basically can be solved. So with these 2 variables, what do you think I'm going to do? I'm going to assume a strain, which means that beta is assumed. For that, I can get the strain distribution, stress delivery, how much stress is delivered, do the summation of the forces. Once I calculate K, I can go back in here and basically calculate the equation for moment and also the curvature. So basically, one has to go through these little triangles and rectangles and trapezoids and calculate their areas, which is nothing. It takes time, but if you're diligent, it's just basically very easily you can develop it. That would allow us to generate the moment curvature, which captures how one goes from one zone to the other zone. So transition from one zone to the other zone is shown by the cracking, as shown in this figure. And that's a bilinear case. Also, there is one extra trick that I do, and that is when I calculate my force equilibrium, which is basically integral over the area of the stresses over the entire depth, I break that up and I save it as 4 separate forces. Force in concrete in tension, force in concrete in compression, force in steel in tension, force in steel in compression. This is a rectangular stress block. I know that these 4 numbers add up to each other and give 0, but I want to, at the end of the day, I want to measure how much force is there in each one of these phases, because that would allow me to calculate the force efficiency factor as defined in here. So the force efficiency factor is a force that's calculated in these equations for the value of the moment, and then I can calculate the moment, I can calculate the curvature, and the beauty of this approach is that everything is parametric. All I need to do is to multiply this parametric m prime that I get out of the solution by the cracking moment, and that gives me exactly the moment. Cracking moment is a function of geometry. So if I just simply change the size of this beam and just change m prime by the amount of steel content, I can easily calculate the moment curvature, and I would have the solution. So the track that we could go, for example, for a specific case is you go through tension cracking, then you start getting steel yielding, or in tension, or concrete compression. So you can go through this path as many as out of those 4x2x2 combinations, and that would allow you to construct your steel design, your steel amount, what is the yield point, what is the transfer from one mode to the other mode, because you're always looking for the minimized moment from all of these competing mechanisms. So the dashed lines are competing mechanisms, whereas the solid line is the minimum value of the moment that the section can carry under this assumed value of these interactions. So we have published these data, goes back to when Professor Yao was working with me. We did about 5 or 6 very popular papers that basically we showed exactly how these zones interact with each other. And these zones basically becomes our limit states. So for a structural engineer doesn't need to know what stage 4142 is. The structural engineer needs to know that this point corresponds to the yielding of steel. This point corresponds to the initial cracking of the concrete where the load is transferred to the steel. This zone is the instability that the case curve comes down, because steel has to be loaded to carry the load. And this becomes really important in our design. So this is basically now we can apply the model to reinforced concrete. To hybrid reinforced concrete is one where we start putting fibers in there to build up this tension zone, because we can run it with only just tension being linear elastic, and we get exactly the standard equations that we teach in our classes. Or if you go to hybrid reinforced concrete, now you have a strain hardening effect. So for something like this, we need a quadrilinear model, meaning that there are 2 zones in the pre-peak and 2 zones in the post-peak if we want to apply it to UHPC. But the bonus that we get from this calculation is that we already know what our limit states are, and we can use those limit states. We have software that have been available. They can be downloaded from ResearchGate, or ask Professor Yao for sharing it with you, or Anling Lee, who was also another postdoc who came and worked with our group. from Professor Zhu's, Deju Zhu's group. And these models have been going around, and we've been trying to build them up because I think that this is a good instructional procedure to show how we can predict the load deflection results, how we can get the moment curvature to put it in. Recently, we've worked on actually making them more user-friendly, where the parameters are input, and we can get the strain distribution and stress distribution. And if you look at this curve, you can see that it really doesn't matter how the shape of the curve is. We get all of this concrete, which is more than 70% of the depth of the material, carrying 2 megapascal. And 2 megapascal multiplied by this area that we have far outweighs how much force your steel is carrying. So that's how we get our load deflection plot with exactly at any point along the curve. You can choose the strain and actually find out where you're sitting on the curve. I feel that this is a much better way to teach and to educate our students that you can actually benefit from all of this concrete, that you're ignoring it. And that's a waste. We need to calculate, and I would love to work with some of our colleagues there to look at the life cycle cost analysis of how this model can help us develop an efficiency grade based on carbon footprint, how much we're helping change the carbon footprint of concrete. And we can do it basically for softening or hardening. If you have experimental data, what you can do is fit this curve to the experimental data and actually get your tension model and compression model. And I can show that here. So for example, this is for UHPC member. This is out of a paper in ASCE. This hasn't been published yet, but basically what it does is that we can do the fitting of the tension, fitting of the compression, fitting of the steel, and then build up these 3 models to actually simulate the results of a reinforced concrete beam that has been made with 2% fiber and a row of 0.85%. But not only that, we can actually calculate the states of stress, show how the neutral axis is moving up and calculating. So here is a mechanical characterization. So we do the material testing, we measure the material properties, and now we have closed form solutions that we can apply to a whole bunch of different structures, whether it's a column, it's a beam, it's a slab, if it's a tunnel lining, and so forth. So we have been looking at these tests for non-proprietary UHPC mixtures for bridge rehabilitation. What you see here is that the bridge that we replaced it in a matter of a week with precast sections, and we poured the connection pour with UHPC. So here is a test method that we did to calculate the load deflection result of the UHPC, back calculate the properties, and once we back calculate the properties, so I've written the actually the DOI for all of the papers that I'm citing here. We can actually measure the strain softening response or strain hardening response. You only need about, with 1% fiber, you only need about 5 megapascal tensile strength and this large range of softening to be able to get this response to go there. So with 3% fiber, this is the curve, the stress strain curve changes, but still we get much better performance. So these are some pictures of the fact that you can replace a bridge in 3 days was completely, it's just like wonderful, especially in some rural areas where an entire community depends on a bridge to be able to be accessed. So these are some tests. Let me see if I can show this video. So this is basically the same UHPC beam that's being tested. And what we can show is that the amount of load that we get basically stabilizes as the crack is propagating. Of course, we're using DIC and all of the tools to be able to show that this residual capacity that we have allows us to reliably expect that the beam is still safe under the load that has been applied onto it. And we can go on. I've been working in this area of precast tunnel sections where we're only using fiber reinforced concrete right now for all of the tunnel lining that are being used. And in our laboratory, we've built up a facility to basically test the flexural capacity and also axial capacity of these tunnel lining. These are using fiber concrete, somewhere about between 30 to 50 kilos per cubic meter. And the response that we get is again the same. Test some standard flexural beams, measure the material property, and you can test the large scale and go from the small scale to the large scale. So this is great for design if I have enough fibers in there to be able to carry the load based on the stresses that are allowed. This has been published. This report was published in 2016, and the method for back calculation. But then at the same time, we also are working on developing a design guide for a code for the design. Quality control becomes a problem because we have a lot of scattering the data when we're looking at it, and that's very scary. For a person who hasn't used fiber concrete, this becomes very scary. But what we are showing is that, and this is about somewhere about 817, somewhere about 2,000, almost about 1,200 data points, 1,200 individual specimens. That was a quality control for a year and a half of a bridge project. So here's a problem. People would say that, oh, you have to calculate characteristic value of these, and then you look at the standard deviation and reduce the data by standard deviation. And my answer is no. This is because the fiber distribution is random. We don't need to really worry about how the results are coming, because what we need to do is to look at the fact that the first crack strength, first of all, if you plot the first crack strength as a function of residual strength, it means nothing. The cracking is a stability condition, first crack. What matters is that we get this, I call it a shotgun approach, that basically is all over the place. Don't worry about this, because that's the initial cracking. Our design should be based on taking all of this data and fitting it individually to measure the tensile stress strain diagram. Then we take this stress strain diagram and calculate the average value of it, not the standard deviation, just the average value. Because when we calculate the stress distribution, oh, wait a minute, I got to go back to one of these previous curves that I showed and discuss it based on that curve that I showed you. When we look at the stress distribution across the section, for any strain along the length, I'm getting the almost similar stress. So the variation that I have along here naturally dies out when I calculate the moment due to here. So that is the averaging process that would allow me to measure the response of the large scale specimens versus the small scale specimen. So this is a small scale specimen, large variation. This is a large scale specimen that has a much lower variation. And it's actually, this is what goes in service, not this one. So why am I penalizing this with this? And this is, again, it's part of our research that's ongoing now to show that there is nothing wrong with getting values this way. Because if you do a Monte Carlo simulation of these data, you can show that your results actually fall very much in a narrow band. Another project that we did was for our light rail system, Valley Metro, which allows us to replace all of the rebar with steel fibers, and we subjected it to 2 million cycles of fatigue. So first you crack it and then subject it to the fatigue situation of multiple loading. This would meant the significant amount of cost savings from the point of view of potential corrosion problem because of the DC current that exists, and that creates stray current corrosion. So if I take the rebar out and put fibers there, I have significantly reduced the task. And this is 3 times the load that would be expected. So we continued this test for 2 million cycles, and here you can see the crack opening as a function of the crack opening as a function of the cycles of the loading. And then basically they just switched over to the fiber case, and that way we got rid of the temperature and shrinkage control. What is interesting in this design, again, I'm running late on my presentation. If you look at the original design, per mile, the cost was $17 million because every single rebar had to be welded. It had to be inspected. It had to be delivered to the site. It had to be set up. So it would take approximately 231 days for a mile of the track. When we switched to fibers, we reduced it by more than half the number of days required, and the cost reduced by $12 million. More than 60% cost reduction per foot of the track can be calculated or the total, simply because we took all of the rebar out in terms of number 4 rebar and number 5 rebar, and we replaced it with steel fibers 2-inch long. This is where we get the effect. And when we look at the sustainability aspect, also we can look at, these are some recent experiments that we analyzed. This is a tension stiffening case where you my microphone was muted. So basically what we get is we get this. Now I think I'm back. Basically what we get is this instability, localization effect now replaces with fibers, and the fibers activate and your stiffness is significantly higher than 1%. Please pay attention. I'm taking 1% rebar and I go to 0.4% or 0.6%, and my stiffness is still increased with the amount of fiber. So this is the synergy of the improvement that we get. And if we back calculate how much load is carried by the matrix, we can see that when you have steel, this is the magnitude of the steel, and the matrix load is much higher. So for a large range in strain, the matrix is carrying a lot more load than the steel, although the matrix has already cracked. And so this is, again, another paper that we just published it in Construction and Building Materials just recently on the tension stiffening effects and the effects of that. Textile Reinforced Concrete is, again, another area that we have published significantly with Dr. Yao, and that shows that we're using the same mechanisms to be able to do distributed cracking and monitor the crack width and the crack spacing for different types of systems. So here, the TRC actually allows me to design it in tension with 15 megapascals. And we have measured the crack width, the size of the crack width, and how we can actually generate the distributed cracking in our systems. Another area that we've done is going with W sections, angles, channels, and in all of these systems, what we're using is the model that we have to be able to simulate the results of the tension and the flexural response. Sandwich composites, all of these systems fit into this design methodology that we have developed using the flexural model that we have, whether we're using, if we use different control points, now we can do sandwich, we can do W sections, angles, and such. So the solution strategy is now developed for us to be able to make W sections with textile reinforced concrete or with UHPC and test them in tension. So these are some of the publications that have come out from our work in the last 2 or 3 years that I should base. So these are all the design equations that basically give us the moment curvature relationship that can be put in a in any finite element calculation or by closed form type solutions. We can apply the same model even to steel sections and exactly fit the elastic plastic yielding in steel. But ultimately what we have is the fact that we get a benefit of the fibers, which is shown in red, kicks in when the steel is taking the time to capture the load. We still need steel rebar, but if we add it with fibers, all of a sudden we get this synergy that the load on the steel is significantly reduced and the fibers carry the load. And we've shown that with panel tests. And actually, again, we can calculate simplified equations for very simple equation that for undergraduates, it's done in a spreadsheet. And all of the parameters can give us the efficiency of the system in the section, in tension or in compression. And we can see that now we're getting a lot more load out of the concrete. This is actually to scale, drawing to scale of a concrete with the tension force compared to the steel rebar. For 100 years, we've only depended on the rebar. I'm begging you to consider that we would also take use of this area of concrete that we're putting in there and calculate these efficiency. All of these equations are in closed form, which means that for any section, we can calculate the properties, and they have been validated. I should skip some of the work about compression. I need to acknowledge the colleagues that have worked with me over the last 5-6 years in these areas, and Yiming, you're there too. So, so basically, there are near future opportunities that we have. How do we implement these design guides into as a low-hanging fruit, and how we can reduce the carbon footprint of steel, carbon, concrete materials, and how we can make low-cost materials with 1/3 the volume of the concrete that we're using. I should stop here at this point and see if I can address any questions you may have. Thank you.
Thank you. Professor Mobasher gave a very comprehensive review on the development, testing, and modeling of fiber-reinforced cement composites, and given some case studies on the beam slabs, walls, and the tunnel linings, and so on. This presentation reminds me of my 6 years of life in Arizona. So many contents are very familiar, and there are so many new stuff in here. I missed some of them. Okay.
I'm proud of you. I'm proud of you.
Thank you. Thank you. Okay. Now it's time for questions. If the audience have questions, you can. Very familiar with the software. You can. I think there's a button that you can raise your hand and open the mic for you. And also, if you want, you can type your questions, and I can. All right. So there's one. Let me see. How do I do this?
I think there is a chat that they can put in questions, and we can look at some of those. You can choose some of the questions, and then I can answer them. Is there a group chat so everybody sees the question?
Okay. So how do I?
I have the screen, so I don't know how to. Let me see if I can.
Here, I see.
Is there a chat more?
Yeah. How do I do this?
React, raise hand. Okay, we have one. We have one hand raised. Mr.
Yeah,
Sean.
but I don't. Okay.
See it, or should I stop sharing so you can take over?
I'm not sure how does this work. Okay, yeah, I can hear you. I think you can speak.
I think why don't you, if you can allow Mr. Zhang to unmute him. If you can unmute him, then he can ask his question. That would be because there is only one person right now asking, right? Can you do that or not?
No, I don't have that option.
Do you see the screen? Rui Zhang.
Yeah, I see him, but
you have to click on his microphone.
No, nothing happens.
Oh, let me stop sharing. Maybe it would be. Let me see. There is a chat.
You should open your microphone on your side.
Pardon me?
I'm talking Dr. Zhong. You can do that yourself.
Yeah, now you can talk.
We hear you now.
Okay, let me try. So, can you hear me?
Yes, I can hear you.
Okay, okay. Hi, Professor Mobasher. So, nice to meet you again. So, I'm not quite sure if you still remember me. I'm the student of Professor Kai Wheeler.
Oh, yes.
And
yes.
we met last time at the UHPC conference. And
yes.
yeah, so it was a very nice presentation. So I benefit a lot. I did learn a lot from this presentation. Just a general question, so nowadays what do they call it? The carbon neutral is a very hot topic, right? So
yes.
Like the textile reinforced concrete, and also like what I'm doing in UHPC, one of the concerns is the sustainability. I mean, the carbon footprint basically is relatively high compared to conventional concrete. So, so based on your experience, what's the direction or what's the efforts can be done to reduce the CO2 emission of the textile reinforced concrete?
For textile reinforced concrete, I think we need to look at the specific strength of the material, because what we are dealing with is a material that has a tensile strength of somewhere around 10 or so megapascals, whereas an ordinary concrete doesn't have any of that. If you're designing a reinforced concrete, let's say you want to design a beam for a given load, and somebody has to sit down and do the calculations, both for textile reinforced concrete and also for the same load, calculate how much material you need and replace that material, compare the two materials from a volume point of view. There are two ways you can calculate it. One of them is a stress ratio. In other words, what is the specific strength of the material? That would be in megapascals per unit volume. And the other one is how much load can be carried by what volume. So that's how we can do our factor that would be multiplied by the total carbon that's put out. Definitely with textiles, the cost is going to be higher because of the processing cost of the textile. But please look at the plastics. Right now, we have an opportunity to recycle plastics, to be able to make fibers, polymeric fibers, and those polymeric fibers can be designed for use in the concrete. The problem right now, the recycling industry is not very strong, in my opinion, is because you cannot recycle them indefinitely. You can't recycle, let's say, polypropylene 6 or 7 times. It becomes useless. You can make water bottles with that. But if you make fibers, you only need to make it once, because the design life of a fiber concrete is like 50 years compared to a 10-minute design life that you have for a water bottle. So of course you can recycle plastics for water bottles, but you can have a system or have an industry that would only say, we're going to make fibers for concrete with all of this recycled waste that we don't know what to do with. Recycled electronics, they can go in there. So it doesn't need to look nice. It shouldn't be like a car component. No, but it can be a fiber that's ugly, but it's stiff. It's good, so we can use it. So that's my idea. But we need to look at both from a design point of view and also from what opportunities are there for us to be able to make these types of materials.
Yeah, I agree. So one way is to like train. I think the engineer need to be well trained, educated to know how to design this specific concrete, and also, I mean, the plastics can be recycled, right? So that are two solutions. Yeah.
So that's a challenge that we have.
Yeah.
That's our challenge.
I mean, yeah, that's a relatively challenge compared to, I mean, steel fibers. I mean, there are a lot of applications for the recycled steel fibers right now.
Yes.
But for plastics, I'm not quite sure how the degradation of the properties of the recycled plastics compared to the original one. I mean, I'm just wondering if you have any idea or any data about the.
I don't. I have colleagues in industry who are making fibers, polymeric fibers. Their plants are running 24/7. In other words, they can't make enough of the fibers. So, in other words, there is enough materials for them to do it. But if we can, my argument here is that if we can use a material that has no path for, it has to go to landfill. So instead of landfilling it or putting it in the ocean, if we can recycle that material, and if we can get about 1 or 2 megapascal, it's better than 0. I mean, it's infinitely more efficient if you go from 0 to 1.5 megapascal residual strength that you can work with it in terms of design. What I'm saying is that we're not losing anything by adding fibers to the concrete. If we can get those fibers cheaply and economically developed, and we can show definitely that our carbon footprint is going to be improving. I think we need good life cycle cost models that are not calibrated against compressive strength. This is the problem in the cement industry, because everybody is looking at life cycle cost from A1 to A3, meaning that when the steel leaves the rebars leave the manufacturing plant, or when the concrete or cement leaves the plant, they stop and say, this is our carbon footprint. No, how much cement are you using per 10 megapascal, effective stress? That's what matters. And that's what we need to calibrate. It's like the mileage of a car. It doesn't matter how big the tank of the car is. It matters what kind of an efficiency of miles per gallon or miles per liter we get out of it. It's all in the calculations that we do, which we cover the real problem and we don't address the real problem. It's the efficiency of our structural system that we should address. So my point is, a 100-year-old methodology has brought us to here. It has humans have lived on that equation for 100 years. Maybe we need to start relooking at it and say, we can design it better by putting another rectangular block for the tension and designing. That's what I'm saying.
Yeah, I totally agree. So I think we need to change the perspective of the engineers or the designers, how to evaluate life cycle CO2 emission or something like that, right? So not just how much concrete or how much cement you use at the very beginning. Yes. I think that's not fair enough for such kind of advanced cementitious composites. Yeah. So
all of the go ahead.
Yeah, go ahead.
No, I just wanted to say that there is so much opportunity for carbon footprint reduction, and people take CO2 and pump it into concrete, and they say, oh, I put CO2 in the concrete, now it's staying there. No, it's not going to stay there. You can't be you can't be capturing CO2 in a fresh concrete. It's not going to stay there. So there are opportunities that we need to be able to tell everybody that the proper way of carbon sequestration is to reduce our consumption. Initial consumption. In other words, the amount of concrete that we use for a given amount of load should be mandated to meet certain types of criteria or certain types of efficiency. Otherwise, we don't get it. We don't have a good answer.
Yeah. So, may I ask a follow-up question? Just so what's the current status of the recycling of the plastics in concrete in the United States?
Not as much, because you really need to have the science behind it. In other words, you need the investment by chemical companies, by petrochemical companies to invest in basically recycling plastics I mean, that's one area. We can do basalt fibers. We can do, I mean, so the technology is there for basalt fibers. Technology is there for glass fibers. Even for steel, we can do that. But the cost, of course, is high. What I think is that, plastics may provide us with a shorter path to the solution of the problem. That's why I focused a lot more. I'm not that much interested in carbon fibers. I'll be honest with you, because the carbon fibers are made for the aerospace industry, for lightweight construction. The size of the carbon fibers, if we can make them for use for concrete, I'm all for it. Because what we need is, we don't need 20,000 filaments per yarn. We need to have it much, much smaller. And maybe we don't need to meet the quality control requirements that meet the carbon fiber for the aerospace design, because that's a very, you can't accept the type of risks that we accept in the construction industry in terms of, it doesn't make sense to use a material that has a perfect, really high, no standard deviation almost, for fiber, whereas your cement and concrete and aggregates are all over the place. So that's foolish. That's foolish, in my opinion.
Yeah, I think that's also the trend occurring for UHPC community. So originally UHPC used very high quality materials, and right nowadays we use recycled aggregates, like all kinds of SCMs, something like that, to
exactly,
because we don't need the 150 megapascal compression.
Exactly, that's my point. We need to work on the tensile properties. I mean, Professor Yao, he worked with me on that UHPC project. We can make it with local materials. Any community can make UHPC. You don't need to sit down and pass your sand through sieves, very small size. No, you can control it, and you can get quality tensile properties that would help you with the overall load capacity of a section. That, I think, is the most important part. If we can make high-grade steel, so the high performance steel rebar can be used with UHPC, and we don't need to pay, $5,000, $10,000 per cubic meter. No, that's too expensive. We can bring the cost down by relaxing some of the criteria. You don't need 6% fibers. 2% fiber would be more than enough for a lot of the applications that we have.
Yeah. Yes, I agree. Yeah. Okay, I guess I don't want to take too much time. I think thank you for your opinions. Nice to meet you. Actually, I'm currently in the United States.
Sure.
Yeah. So maybe I can visit you someday, because I'm
definitely. I would look forward to it. Yes.
Cool.
Yes.
Yeah.
Great.
Thank you.
Thank you.
Yeah. Okay. Any other questions? Actually, I have one. The one thing that stops people from using UHPC and other kind of high performance materials, especially probably it's the same for other countries, but especially in China, it's the cost.
Okay. It is the cost.
I noticed
Go ahead.
Yeah, and there's a slide showing I think it was the tunnel lining no, not tunnel lining. I think the railway project. Yeah. It's showing the cost compares the cost. Okay, I think it is about the labor, right? So save on the labor cost.
You save on the labor, but then at the same time, if you're replacing a bridge, many times, I have a lot more pictures and such that I can share with you on the bridge. You need a very small volume of UHPC to repair a bridge, because if you're making precast concrete bridge decks, those can be made with ordinary concrete. It's only the connection points that you're using UHPC. And as long as your UHPC is designed to meet a strength requirement that makes it stronger than the other components of the bridge, then you're fine. So you might only need for an entire bridge, like the ones that I showed you, we only needed about 7 or 8 cubic meters. That's it. So it's not like it's just 1 or 2 trucks, small trucks for one bridge. But if instead of waiting for 2 months or so to repair a bridge and the traffic diversion, and you have to basically provide for safety features, for the what's called user cost. In other words, how much people stay behind the traffic for that bridge to get repaired. All of those are costs that once we add those up, we find out that it makes a lot of sense to use UHPC. Pay a little bit more upfront. We shouldn't compare UHPC with ordinary concrete. We should see what does it take to finish this project from start to finish using UHPC or using the traditional method that you have used before. So that, I think, makes a lot of sense. Planning makes sense. Getting the experience makes sense. People like it because it's actually labor is significantly reduced. You don't need so much rebar in there because the fibers, with just 1 or 2 rebars, the fibers are just basically going to give you that interface bond and they carry the load. So it's going to pick up. I'm sure we need design equations. That's what we're working on. So the procedure that we're working can be used for somebody to sit down and very easily design and find out that, yes, they can carry it. And you can do it in your lab. Design it with with this software and check, see, how the results look like. Once we gain the confidence, then we can apply some safety factors and then go forward.
Yeah, great. Okay, I think we should work together on a paper also on the cost on the carbon emission.
I think I would really love that opportunity because I've been really trying to learn more, but we need to do it from a fundamental point of view, not just a lot of people are industry experts in life cycle cost, but they don't know exactly how we can look at it from a structural point of view. We can actually design it for the same specific value and show the efficiency of the material. It doesn't even have to be UHPC. It can be just fiber concrete with 1% fiber. That would work also. We have the limitation. We don't have to be limited with, the cost of super plasticizers and everything. The good thing about UHPC is that its durability is very much good. So for bridge decks and things as such, we don't have the corrosion problem. For tunnel lining, we don't have that problem. But right now, I can say that in US, almost 80 to 90% of all tunnels are using fibers. No rebar, purely no rebar, only fibers. Because it saves so much cost. Because this shape of these, curved shapes, bending rebars for them to tie together, that is labor. And you need expert labor. The tolerances, and even if you do that with rebar in the tunnel lining area, you have to provide for cover concrete, and that cover concrete is not reinforced, which means that as long as you have TBM machines pushing on it, you get compression. The compression forces cause the failure of the cover concrete. So that's the problem. And then you get moisture, you get water coming. So I can send you the papers that we did on it with polymeric fibers meeting the same criteria that the steel fiber meets. And that makes a lot, that's a lot cheaper actually, and blends a lot easier and flows easier.
Yeah, I think we should plan that, and we can talk about this later. Okay, so, and if there is no other questions, I think it's 7:30 your time and 10:30 meeting time, and I think it is on time, right? We plan 90 minutes of the whole presentation. And
okay.
So if there is no other question, let's thank Professor Mobasher again for giving
this. Thank you so much. Thank you. I appreciate it. And stay in touch. We should collaborate.
We learn a lot. Okay, so if you guys have any... Okay, so if the audience have other questions, you can send email to Professor Mobasher directly, or you can talk to me. I think a lot of students can. Yeah, you can talk to me as well, and we can communicate afterwards. Okay, all right. So thank you again, and have a nice evening, I think, right?
Thank you. Thank you all.
Thank you.
I appreciate it.
Okay.
Okay.
Bye-bye.